Hello and welcome to Gaffy's Grinds. This is video 6 in our series on radioactivity for leaving cert chemistry. In our previous video, we learned how to write equations for the alpha decay of different radioisotopes. So just as a quick recap, before we begin today's lesson, today's lesson we'll be learning how to write beta decay equations. But before we do, I want you to just see how much you remember. So without looking back from memory, I want you to try and write an equation that describes the alpha decay of radium 226, radioactive isotope of radium. All right, so what I want you to do is I want you to pause the video and I want you to try and write that equation. A reminder, if you don't do the questions when I ask you to, you're not going to learn anything from the videos. So pause the video and do that now, please. Okay, this is what you should have. The first thing we need to do is we need to write down what we're starting with. We're starting with radium. Radium's chemical symbol is Ra. That's radium. It's got an atomic number of 88. You can find that on the periodic table. And its mass number for this particular isotope, because it's radium 226, it's got a mass of 226. Now, if you didn't know that and you didn't know how to get it started, you have another opportunity to pause the video and do it now. Do the rest now. Okay, so you should only be watching if you now have a finished equation. Okay, well, what are we going to produce? Well, it's an alpha decay. So we're definitely going to produce an alpha particle. What do we know about an alpha particle? An alpha particle has an atomic number of 2 because it's got 2 protons, and it's got a mass number of 4 because it also has 2 neutrons. So altogether the mass is 4. Next thing we need to do is find out what will the new nucleus be. So we need to take our mass number of our radium that we're starting with, 226. We're going to take away the mass of the alpha particle, gives us 2, 2, 2. Then we need to take our atomic number of radium, which was 88. This was the nucleus of radium, but we've now lost 2 of the protons there. So now we've got 86. So what's left over? Well, we've got to fill in these 3 boxes. We need 2 numbers, an atomic number and a mass number, and we need a symbol. So our atomic number is 86. So let's find the element on the periodic table that's got atomic number 86. And when we take a look, you'll see that it's radon, or N. So a different nucleus is now a different element. The nucleus has changed. Okay, so this is definitely not a chemical reaction. We've got a new element here. That doesn't happen in a chemical reaction. Our new atomic number is 86, and our new mass number is 222, like what we calculated down here. Well done if you got that right. So that is alpha decay. In today's lesson, we're going to be looking at what happens during beta decay. So remember, what is a beta particle? So speak your answer to the screen on 3. 1, 2, 3. A beta particle is a high energy electron. So what I'm going to do is I'm going to draw an unstable nucleus. So this is a large nucleus with lots of protons and neutrons, and it is unstable. It's unstable because there's too much energy in here and the number of protons and neutrons are unbalanced. So here I've got protons and neutrons. Now, this particular isotope will say it belongs to iodine 131. This is a radioactive isotope of iodine 131. If we check this out on the periodic table, the symbol for iodine is capital I, and the numbers, well, iodine's atomic number is 53. And obviously, if this is iodine 131, then we're talking about the iodine atoms that have a mass of 131. Okay, so what happens during beta decay? What happens during beta decay is this guy here, one of the neutrons. One of the neutrons, this is a neutron, so we're going to draw it with a green dot. This here is a neutron. Okay, a neutron. And a neutron splits to produce a proton. That sounds crazy. This is the first time you're ever hearing that this can happen. a proton plus an electron. And that electron is immediately kicked out of the nucleus as a beta particle. So what leaves the nucleus is a beta particle, which is a high energy electron, a beta particle. So this is this high energy electron that gets emitted from the nucleus. And it's emitted, this electron is emitted from the nucleus as a beta particle. So sounds crazy. A neutron splits to produce a proton and an electron. The beta particle has a mass of 0 because it's just an electron, and it's got a charge of -1 because it's an electron, and electrons have a -1 charge. So that sounds quite strange and unusual. Now notice, this is not one of the electrons that is orbiting the nucleus that we would normally draw, where we have the nucleus and we've got around the nucleus, we've got these shells of electrons. This is not one of those electrons. Those electrons stay where they are, they don't change. A beta particle is an electron that begins its life in the nucleus. Okay, so it's a neutron that's made up of a proton and an electron stuck together. And a neutron splits, kicks out the electron, and the proton stays where it is. Okay, so crazy stuff going on. It's the first time for sure you're hearing about that. So just going to go through that one more time. A neutron in the nucleus splits to produce a proton, which stays in place, and kicks out the electron. So kicks out a negative electron as a beta particle. Let's have a look at the nucleus. What's going on? Well, obviously iodine normally has 53 protons, sorry, because its atomic number is 53. It normally has 53 electrons because the charges have to be the same. And it normally has neutrons. It normally has 131, take away 53. So that's atomic number, take away the mass number. That's going to give me 78. So before the beta decay, this is the way the numbers are. We've got 53 protons, 53 electrons, and 78 neutrons. When the beta decay occurs, the iodine splits to produce a beta particle. Let's look at what's going to happen. The neutron up here, the neutron splits to produce an extra proton. So look what happens down here. The number of protons in the nucleus increases by 1. Give us 54 neutrons because a neutron, 54 protons, because a neutron has split to produce a proton. The electron is produced, but it's fired out of the nucleus. And it's not one of the 53 electrons that was orbiting. These 53 electrons are the orbiting electrons. And the atom will still have 53 electrons orbiting. Orbiting in shells. These electrons don't go anywhere. It's not these electrons that move. Okay, so the beta particle comes out of the nucleus, remember. What happens to the number of neutrons? Well, the number of neutrons was 78, and we know that during a beta decay, one of those splits to make a proton and an electron. So that means the number of neutrons is going to decrease by 1. So we now have 77 neutrons. Okay. Now what? So let's just summarize here. Before the decay, and after decay. Okay, so before decay, we had 53 protons plus 78 neutrons. That gives us a mass, a relative atomic mass of 131 is the RAM, relative atomic mass. After the decay, we now have 54 protons, an extra proton, but we have one less neutron, 77 neutrons. Sorry, I'm going to say what that is, 77 neutrons. Altogether, that gives us the same relative atomic mass. 131 is the relative atomic mass. So the mass doesn't change either. Okay, so we change a neutron into a proton. And what effect is this going to have on the atom itself? Well, we started with iodine 131 up here. We have now produced a nucleus that has an atomic number of 54, not 53. So if I go and check the periodic table, the element with the atomic number 54 is xenon, Xe. So we now again have produced a different element. Its mass, as you see down here, is still 131. Don't forget, we have produced a beta particle. -1 is the charge, 0 is the mass. Okay. Right, we're going to answer some questions now. Okay. So first of all, by speaking your answer to the screen, I want you to answer the questions for me, please. So the first question I have for you is, what is a beta particle? So speak your answer to the screen on 3. 1, 2, 3. I hope you said a beta particle is a high energy electron. Question 2, what is the charge of a beta particle? Answer to the screen on 3. 1, 2, 3. Okay, I hope you said the charge of a beta particle is -1. Question 3, where does a beta particle come from? Answer on 3. 1, 2, 3. Hope that you said it comes from the nucleus, from splitting of a neutron into a proton and a beta particle. Right, we're going to do some practice equations now. Okay, so what we're going to do is I'm going to do a bit of another one for you. So let's take a look at another radioisotope. We've got SR, which is strontium, and it's strontium 90, mass of 90, and it's got an atomic number of 38. Okay, so this here is pretty straight. This is a radioisotope of strontium. Obviously, this is going to be a beta decay. So in a question in the exam, you will always be asked, if you're asked to write one of these equations, you will be told that you need to write the beta decay or the alpha decay. So you will know which one you're being asked for. Okay, so obviously we're producing a beta particle. Beta particles have a charge of -1 and a mass of 0. Now, we will also produce this element here. Yttrium has a symbol Y. What I want to know, what you guys need to do, is tell me what are the new numbers. So in this one, all you have to do is tell me the new numbers. So what I want you to do is pause the video, write it down, and fill in the 2 boxes. Okay. Hopefully, you said that the atomic number is now 39, and the mass is still 90. Well done, if you got that right. Excellent, good job. Okay, why? 39, because we have changed a neutron into a proton, so we've added an extra proton, which changes the atomic number. The mass is still the same because the neutron has just been replaced by a proton, which has the same mass, and an electron has been kicked out, which doesn't have any mass. So the nucleus doesn't lose any mass. Next one. Say we start with iodine. Oh, sorry. Say we start with iodine, but it's iodine 131. Did we do this one already? Oh, we did. Okay. So let's see if you guys can remember it. 53. Iodine 131. What I want you guys to do now is I'm going to tell you we're producing a beta particle, which is a charge of -1 and a mass of 0. All right, I want you to tell me the numbers and the element. Pause the video, do that now. Okay, the element you should have written is xenon, and the numbers are 54 and 131. Well done, if you got that right. Okay, good job. The next one I want you to do is we're going to take nickel, and it's nickel 63, 28. I want you to pause the video and write out the rest of the equation for me, the beta decay equation for nickel. Pause the video, do that now. Okay, what you should have had, and you should only be playing if you try to do this by yourself, we should have a beta particle, -1 charge and 0 mass. Well done, if you got that right. Plus, we're also producing a new element. So we have new mass number, new atomic number, and a new element. The element produced is copper. Well done, if you said that. We have an extra proton, so the atomic number has gone up by 1, 29, and we have the same mass, 63, like that. Okay. Just to show you the workings there, how do we do this? Well, we know that the atomic number is going to go up 28 plus 1 equals 29, because this is extra proton. The mass is 63. You can take away 1 if you want for the neutron that's gone, but then you have to add back in 1 because you've got an extra proton. It's essentially just a neutron kicking out the electron and leaving behind a proton, which has the same mass as the neutron anyway. This is why the mass stays the same. Okay, that's where the numbers come from. Last one, we're going to do a beta decay. We've got a beta particle, -1 and 0, and the resultant nucleus, the one at the end, is sulfur 3216. What I want you guys to do is pause the video and work backwards and find out what I started with. So pause the video and do that now, please. Okay, so you should only be watching if you have tried to do that. What you should have is this. The element was phosphorus, a different element, atomic number 15, and mass number 32. You got that right. Well done. Good job. Excellent. You're ready to do some more practice. What I want you to do is I want you to pause the video and I want you to complete the paragraph, but fill in the key words. So don't just write the key words, write the whole paragraph, fill in the key words. Okay, it's really important for making your scientific writing better and linking ideas together. And that helps you learn things better for the long term. So do that now, please. Answers are coming up now, so you should only be watching if you have completed that. And this is what you should have. Pause the video and make your corrections now, please. And well done. If you're getting all of those right, it means you're learning a lot of stuff. Well done. Now, a little bit more. Alpha and beta decay, and I suppose gamma radiation, so alpha, beta, and gamma radiation, are processes which change the composition, structure, or energy of the nucleus. So we know that nuclear reactions, alpha, beta, gamma, all of them are about changes to the nucleus, changes to unstable nuclei. So here I am drawing an unstable nucleus with its protons and neutrons, and we know that there's too much energy in here. They're vibrating quite a lot. The unstable, eventually they're going to do a decay event, and we're going to kick out a particle or some energy out. So we can have alpha decay. Actually, you know what? I'm just going to use the symbol because you guys should know that now by now. You have alpha decay, beta decay, or gamma radiation. But all of these processes involve changes. They all involve changes in the makeup, structure, or energy of an atomic nucleus, an atom's nucleus, in other words. These processes that cause these changes, we call these nuclear reactions. These are nuclear reactions. Nuclear reactions are processes that cause changes in the makeup, structure, or energy of an atomic nucleus. Now note, they are different than chemical reactions. Chemical reactions that we've basically looked at up to now always involve changes in sharing or transfers of the electrons in the orbits. Those are chemical reactions. All our chemical reactions where we mix two elements together and we get a new compound, all of that has to do with electrons orbiting the nucleus. There's an electron, we often talk about atoms losing or gaining electrons. We've talked about atoms sharing electrons. Those are those orbiting electrons, and most of chemistry is interested in what happens to those. But these are nuclear changes. They change the element, they change the nucleus. They don't really involve the orbiting electrons. So these are what we call nuclear reactions. Now let's just compare the two. Okay, so you guys need to be able to compare the two. So say we have chemical reactions and we're comparing them to nuclear reactions, chemical or nuclear processes. Okay, well, first of all, we said that the nucleus involves, if we nuclear, sorry, that should say nuclear, not chemical. Nuclear reactions. Okay, nuclear reactions involve the nucleus, changes in the nucleus. Whereas chemical reactions, mixing two things together to make a new compound, that involves electrons. So, sorry, this should say nucleus. Involves the nucleus, and this involves electrons. And we're talking about orbiting electrons. So chemical reactions involve orbiting electrons. Nuclear reactions involve changes in the nucleus. Now, nuclear reactions give new elements. As we've seen above in the examples up here, all of these, we start with one element, we end with another element. Iodine turns to xenon, nickel turns to copper. That doesn't happen for chemical reactions. We know the law of conservation of matter says that all the atoms have to be accounted for. We can't magically create a new element in the products if we didn't have it in the reactants. So in a chemical reaction, no new elements are formed. You can join elements together to make compounds, but you can't make new elements out of nothing. No new elements. Nuclear reactions involve a lot of energy being released from the nucleus. So we say release of nuclear energy as gamma radiation. So gamma radiation transfers energy away from the nucleus. Chemical reactions involve energy, but we're usually talking about like thermal energy, like heat can sometimes be involved in these types of reactions, but not nuclear energy. There's no energy release from the nucleus. So no release of nuclear energy in chemical reactions. So there's no gamma rays. Okay, and I suppose the last real difference is that chemical reactions, we often talk about bonds have to get broken and reformed. So bonds between atoms get broken. Bonds are broken and formed. Now, bonds are broken and formed. The difference in a nuclear reaction is I was really only talking about one nucleus. I was only talking about one element, nickel. So one atom of nickel can break down to form an atom of copper. It's not bonded to anything else. So actually, there's nothing to do with bonds. So no bonds are broken or formed for nuclear equation. It's literally just the nucleus breaking down. So no bonds are broken or formed. So these are the major differences between chemical and nuclear reactions. So that simple table explains or kind of summarizes the information, but it really is important that you understand the principles behind. Think about the process of what's actually happening. In one case, the nucleus is breaking down and changing. In the other case, in chemical reactions, the nucleus stays the exact same, and we literally just just move around electrons that are in the energy levels. That's chemical reactions in a nutshell. Nuclear reactions actually involve the nucleus splitting up, changing elements. All right, so if you think that that would be a useful thing to take down, you can pause the video and take it down now. Okay, and now last bit of practice to do. And what I want you guys to do is I want you to do these without looking at the notes that you just took down. So cover them over, pause the video, and do the questions, please. Okay, so you should only be watching if you've done the questions. The first one, is this a nuclear or a chemical reaction? Hopefully you recognize that it's a chemical reaction. Next one, how do you know? Well, it involves electrons. As you see here, it involves electrons and there's no new elements formed. There's no change to the nucleus. Okay, so how do you know? It involves electrons, no new elements. You could literally use any of those examples that we talked about. Involves electrons, no new elements, no change to the nucleus, and no nuclear energy given out. Which reactions involve the nucleus? That would be the nuclear reactions involve the nucleus. Which reactions result in the formation of a new element? That would be nuclear reactions. Well done, if you got those right. What is a nuclear reaction? So to define it, so this is your definition. What is a nuclear reaction? It's a process, first of all. And what does it do? It processes that. It changes something. What does it change? It changes the makeup, structure, or energy of an atom's nucleus. That is what a nuclear reaction is. It's a process that changes the makeup. So what it's made up of, how many protons, how many neutrons. So it changes the makeup, structure, or energy of an atom's nucleus. Well done, if you were able to remember that definition. If not, I suggest that you put it on a flashcard or whatever way you have of retrieving things, and make sure you practice testing yourself to see if you remember it very often. There's lots of different ways you can do that, but you need to make sure you're practicing retrieving it. Number 6, use a table to compare nuclear and chemical reactions. So I have that over here. Here is your table. There is the table. So could you reproduce it from memory? If you could, great. Even if you could only do like 3 of the lines, great. Okay. And maybe you'll remember the other one the next time. But the more detail we can remember each time, the better. The main thing is that we're not copying. If you're copying, you're not going to learn anything. Last one. Some people think that nuclear equations are the same as chemical equations. Explain why they are wrong. Well, you can literally use any of these reasons. Why are nuclear equations not the same as chemical equations? Well, nuclear equations or nuclear reactions they involve the nucleus, whereas chemical reactions involve electrons. We don't form any new elements for nuclear reactions. We do form new elements for nuclear reactions, and we don't for chemical reactions. We don't have any nuclear energy released in chemical reactions, but we do in nuclear reactions. You get the picture. So you have to take some of the reasons and say how the reactions are different, chemical and nuclear reactions. How is it that they are different? All right, that's the end of beta decay equations. You should now be able to write. The most important thing from today's video, I suppose, is that you have a general idea of the difference between nuclear and chemical reactions, and that if you were asked to, and you were given a particular element, and you were said to write a beta decay equation, that you would be able to write the decay equation like that there. So you should be able to say before and after and what is happening to the nucleus during that process. Okay, so hopefully that was enough of those to be practicing. If not, if you need more practice, do drop a comment in the video below, and I could stick in a document with a few more practice ones that I could stick in and link to the video if you need more practice. All right, that's it, guys. Thanks for watching. I'll see you in the next video.